So the second speaker of this session is Nu Zhu from Nordea Bank. She will start giving an introduction about Bayesian statistics, and she will continue about two popular packages to do Bayesian inference in Python, PyMC3 and PyStan. We welcome Ms. Nu Zhu from Nordea with a good applause.
Great. Hello, everyone. Can you hear me clearly?
You have to turn it on, and it's on the wrong side.
Oops. It's fine, as long as it works. Can you hear me now? Great. Good morning, everyone. My name is Nu. I have a statistics background, and now I'm working with credit risk in a bank called Nordea here in Stockholm. Today, I will talk about Bayesian models and how they are implemented in Python, in PyMC3 and PyStan. In recent years, Bayesian modeling has improved dramatically with the application of Hamiltonian Monte Carlo and especially non-Newton sampler. Now is a great time to use Bayesian model because we finally have the algorithm to leverage those complicated models. This talk is aiming to inspire data scientists who want to add another tool in their toolbox to those who have the data and want to extract the knowledge using Bayesian techniques. As you might know, there are two excellent packages in Python when it comes to Bayesian inference, PyMC3 and PyStan. When there's only one package, you don't have many choices. But now we have two. What am I going to choose? It's like buying shoes. But I think it's more complicated than buying shoes, or it's worse than buying shoes. For shoes, you can just buy all of them. But when it comes to modeling, you do really need to implement your models in both of the packages. And I hope after this talk, you will have some ideas about where to implement your models. Before we go to the next slide, I would like to say many thanks to my husband, and then I really appreciate all the support from him. I like your sense of humor. In order to enjoy this talk, I would expect you to be familiar with Python. At least you've been using Python, and you use at least one package in Python. It could be NumPy, for example. And when it comes to the theoretical part, it's just entry level. And in this talk, we're not going to talk about Bayes, but we are going to talk about how we implement Bayes models in PyMC3 and PyStan, and to compare those two models, or two packages, I mean. So here's the outline. First, I'm going through basic Bayesian concepts and talk about how Bayes rules becomes Bayes inference very quick. And then I will introduce a generated model, and I will show you how I do this in PyMC3 and PyStan. And I have a more complicated and practical model, which I used data from Allsvenskan. I'm aiming to predict who has the highest probability to win, to qualify, and to be relegated. And I will also have summary, reference, and a Q&A session in the end. So, basic Bayesian concepts. Does it look familiar to you? This one. The Bayesian rule is just a result in probability theory, but together with the notion of prior, cannot see my mouse, prior, likelihood, and the posterior, we got the basis for Bayesian inference. This is posterior, this is likelihood, this is prior. And this denominator is just a scaling factor. And here we don't have to care about it. And we say that the posterior is proportional to likelihood times the prior. So by doing Bayesian model, we add our personal and expert knowledge into our model as a prior. And we also quantify the uncertainty of the parameters. Because here, the theta, our parameter, will not have a fixed value anymore. It has its own distribution. And sometimes it's very hard to, or even impossible to compute the posterior. Posterior can be very complicated. You can imagine those crazy and fancy distributions they put together. So we really need a good sampling algorithm to understand the posterior. That's why we need to use PyMC3 and PyStan to implement our Bayesian model, and they will do the inference for us. Now I'll introduce the first model, a generated model in PyMC3 and PyStan. I generate 50 samples from the normal distribution with mean 0 and mu 1. To the left is PyMC3, and to the right is code in PyStan. And the first part is the same. I just generate random samples from NumPy. Here I generated 50 random samples from normal distribution, 0, 1. And the blue one is the frequency bar. And first I look at the data. First, I look at the data, the x. Let's say my data is x. So it looks like normal distribution, sort of. And I think it is also a good idea to have PyMC3 on board. And now this is the modeling part in PyMC3. I only assign the prior for the mean. This is the prior. It follows a normal distribution with mean mu 0 and a standard deviation 0.5. It is pretty strong. I would say it is pretty strong prior because it looks like this. If it's a weak prior, the distribution will look like this. It means you don't have many knowledge to your prior, to your data. And this is my likelihood. And I run it. I'm compiling the model. It took me less than 1 second. And I'm generating samples using PyMC3. I took 10,000 samples for 4 chains. Each chain I have 10,000 samples, and I have additional 5,000 samples to warm up my chains. So in total, I have 40,000 samples, and you can see how much time it took. And I really like those bars. You can see how long time, how is the process. And you can decide if it's time to have a coffee break or not. And you can see it took 1 minute. And now let's take a look at the code block in PyStan. Here, I take PyStan on board. And this is the modeling code, modeling block in PyStan. And still, you can compare with PyMC3, and you see PyStan is just a string in Python, and it is written, it really looks like C++, and you need to define everything, the length, and you can also define the boundary of your data. And this is the simplified model block. We have data, we have parameters, remember? It's only mu, and my model. And this is my prior, and this is my likelihood. I really like this statistics language in PyStan. It looks really like a distribution on the book. And we compiled the model. It took me 2 minutes to just compile the model. But when it comes to the sampling, I took the same amount of samples as I did in PyMC3. It only took me 1 second. And now let's take a look at those samples. Here is the trace graph of all my samples. If you can see, I have 4 chains, and they have 4 different colors. I prefer this graph than the trace block, than the trace graph in PyStan. It doesn't look as beautiful as in PyMC3. And you can also retrieve your samples from the trace. Trace is what trace contains all my samples. And I can specify, since I have 4 chains, here I only took 1 chain to just illustrate how you can extract samples in PyMC3. And this is a brief summary of my samples, and you see the estimated mean is minus 0.12, and you also got the posterior distribution here. And there are also diagonal features that you can get. And everything here you can easily find here in PyStan. And it tells you how many chains you have and how many effective samples and how good the convergence is. And this is the graph to show how mu changes during the whole process, during the whole samples. And you see our samples are trying to figure out where to go and try to converge. And at the end, it converges. I make this graph just from matplot, so nothing fancy in PyMC and PyStan. And what I did next is just to compare the inference. If you want to do the inference in a frequency way, what do? You just simply take the mean and compute the interval. You see the mean is quite similar to the mean we get. This is the mean. This is lower bound of the 95% interval, and this is the upper bound. And you see the mean is quite close to the mean we got from the Bayesian inference, but the interval is wider. So if you compare the interval here you got from the frequencies way and the interval you got this from Bayesian, you can clearly see that you got more information by doing Bayesian. Now I'm going to talk about a more practical and a more complicated model in PyMC3 and PyStan. Imagine I'm a big fan of football. I want to know who has the highest probability to win, to qualify, and to be relegated. So there are 161 played games and 98 upcoming games when I did this estimation. And this is how my input data look like. For each game, you have a home team, a away team, and you have the score for the home team. I call it home score. And you have the score for the away team. And this is my upcoming games. I have, for each game, I still have home team and away team, but I don't have home score and away score. And those are what I'm what I'm interested in, and I want to do the inference. For each match, the score for here. For each match, the score for home team and away team follows the Poisson distribution with lambda home team and away team. Let's just, for example, if I am playing as Malmö and you guys are playing as Djurgården, I play at home, and in this game, my home score follows the Poisson distribution with my home lambda, and you, as the away team, and your away score follows the Poisson distribution with lambda, your away lambda. But vice versa, if you guys are playing at home, and you will be the home score, or you will get the home score, and you follow Poisson distribution with your home lambda. So this means for each team, you have your home lambda and away lambda. And the next question is, how do I construct lambda? And I used average goals, home advantage, and offensive ability and defensive ability to construct lambda. And my average goals and home advantage are the same for all teams. I think it's the same. But the ability, offensive ability and defensive ability are different across all teams. Does that make sense to you? So those are my prior. My average score follows a normal distribution, and my home advantage also follows a normal distribution, and they are the same across all teams. And for each offense and defense ability for each team, and they follow a normal distribution with 0 and 0.5. Now let's go back to Python. All the previous work, all the works here are just preparing the data for the modeling purpose. Now I also want to, there are steps if you want to do prediction in PyMC3, you need to use Theano. First, you need to input all your input data to Theano as a shared variable, and this is the modeling part in PyMC3. My prior is here, and my lambda. I use those 4 parameters to construct my lambda, and this is likelihood together with the input data. And if you look to the right, and this massive thing is the model block in PyStan. You really need to define everything in PyStan, and it's like C++. But the modeling block is quite standard. You have your data part, and you have your parameters, and you have your model part. This is my prior, and this is my likelihood. And at the end, this time I want to make prediction. And so you have generated quantities. I use this block to make the prediction. And now let's compile the model. I took like less than 1 minute to compile this model, but it took me 3 minutes to compile this massive code in PyStan. And there are more interesting things going on. Now I want to do the sampling and do the prediction. let's first start with PyMC3. I'm taking 10,000 samples and 40,000 samples in total. And it took me 10 minutes. And now I'm going to do the prediction. As I said before, you really need to use shared variable in order to do the prediction. And here comes the most beautiful part. And it took me like half an hour to do the prediction. So together with the sampling and the prediction, it took me 40 minutes. I could go to the gym. But on the other hand, in PyStan, it took me only 1 minute to take the same amount of samples, 40,000 samples, and to do the prediction, only 1 minute. And what I'm doing in the following, here you can see my parameters, average, goals, and home advantage, and the offense ability for 16 teams, and the defense ability for 16 teams. It's quite similar if we compare PyMC3 and PyStan. And guess who's the winner? Here you go. This is the result. I imported the result from Python. Just copy paste to Excel file. I made this in Excel file. And you see, to the left is my outcome from PyMC3, and to the right is my outcome from PyStan. And both of them said, okay, Malmo has the highest probability to win, and those two poor guys has the highest probability to be relegated, and Sundsvall has the highest probability to be qualified. So to sum up, what I did today was to quickly introduce Bayesian Inference, and I illustrate two models in both PyMC3 and PyStan. One is very simple and generated model. One is using practical data, real life data. And let's just sum up the difference between PyMC3 and PyStan. PyMC3 relies on Theano, as you saw before, how I did the prediction. I really need to use Theano. And the PyStan is just an interface, Python interface of Stan. And when it comes to language, PyMC3 is fully written in Python, while PyStan, as I mentioned before, is an interface of Stan, which is written in C++. So if you never used R or C++ before, the model block in PyStan can be a bit overwhelming or massive for you. And Stan, you can use Stan in other environments. It doesn't only apply in Python. You can also use in, let's say, for example, R. But the PyMC3 is just a Python package. And sometimes you want to write dynamic model. As you seen before, the model block in PyStan is just a string in Python and then compiled to C++ code. And if you want to make the model more dynamic, you can use string operators. But when it comes to PyMC3, you can just write in normal Python language. And community, I like it. You can find the modeling cases or examples in both communities. In PyMC3, you can directly find those examples in PyMC3 docs, while in PyStan, you need to go to Stan and find cases. And those cases are not usually written in Python, and sometimes they could be mathematically heavier than PyStan. And another nice feature of PyStan is it has an around 600 pages user manual that you can read. It contains everything, like the language of Stan and what kind of distributions they have, and etc. And it's very comprehensive and very, very well written. And for me, PyMC3 docs, it's just like an IKEA instruction book. it's simple and ready to go. When it comes to performance, as you think before, in PyMC3, it takes almost no time to compile, but it takes a lot of time to do the sampling and the prediction, especially when the model is big and the sampling size is large. But when it comes to PyMC3, it takes time to compile a string to C++ code, but takes almost no time to do the sampling and prediction. So no coffee break for you if you want to use PyStan. All in all, packages are just assist us to realize our modeling dreams, and it just assists us to explore the data and to explore the areas that we are interested in. What we really have to work with is to explain the models, is to build the model and to explain the model. Both of the packages have state-of-the-art sampling algorithms we need, and people are different. I cannot just say this is better than that, but I hope now you have some ideas about where you're going to implement your models, your Bayesian models. Here are some nice stuff that you can read and watch. Thanks. Any question?
Yes. The fact that performance home and away needs to be modeled with two different models. Is it a wide known fact, or is that something you found out?
What did you say?
The fact that the models need to be different for when a team plays a home game and an away game, you model those with two different models, or at least two different Poisson parameters there. Is that a wide-known fact, or is that something that you found from the data?
I didn't find out this from the data, but I think it's quite, it's like a common knowledge. For me, it's like a common knowledge. Because you perform slightly different when you play home and when you play away, because you gain more scores when you gain more points when you play away if you make a goal. And also, modeling is quite private. I would say you have your own preference. So if you would like to model away ability and home ability in one model, you can also do this.
How accurate do you think your model is? How does it reflect the real life? And would you bet real money on it?
No, well, we can see the results quite soon, I guess. You?
So you showed PyMC3 having quite a lot worse performance once the compile step was done, but you said it was using Theano as a backend. Does this mean it will run quickly if you have a GPU available? So sorry, the question of microphone was given that PyMC3 says it uses Theano as a backend, or at least can. Does this mean you can get much better performance if you have graphics cards, GPUs, whatever, available?
Yes, I am.
And does Stan take any advantage of better hardware there?
I am actually running those models in Linux system. And my poor computer doesn't have a GPU, so I've never tried running my models in GPU. But I've heard that you can do Theano in GPU, and if you want to test, I would like to know if it will increase the performance or not. Thanks for your question. Any more questions?
Thanks for the talk. I was wondering, is it common to do Bayesian analysis from Python as opposed to R or other environments?
It's a difficult question, I have to say. It's hard to say what is common, what is uncommon. And you can do Bayesian, if you're a Pythonist, you would like to use Python, I guess. You can also do Bayesian inference in something called Buck. It's not a good name. And you can also do it in R or just in Stan. But it's just a personal preference. As a Pythonist, I guess you don't want to If you want to do the model, you don't really want to go into another environment to learn another language and do your model. Does that answer your question? Yep.
Is there a reason why you didn't use scikit-learn? Because that is a really good package as well, and it has a lot of information and good documentation on it as well.
I have never used scikit-learn, but for Bayesian inference. I think the reason why I use PyStan and PyMC3 is both of the packages have the state-of-the-art sampling algorithm, and both of them can use non-Newton samplers, which is an updated version of HMC. And in PyMC3, you can also choose other sampling strategies like Metropolis or Metropolis random walk or slice. But in PyStan, it is only for nuts, non-Newton samplers.
And is there an alternative to Bayesian inference for this problem, let's say? Can you do it with another machine learning algorithm so you don't have to, learn all these statistics?
I like your question. I really think there's another way to build this kind of model, not this kind of model, to let's say, to know who will win, who is the winner of Allsvenskan. But in this forum, we're talking about Bayesian, and I haven't tried to use other machine learning techniques to draw the conclusion. But if you're interested in to implement this model in another approach, please let me know your approach and your result. You have my email there. Any more questions? Good. Thanks for your patience, and I wish you have a nice day.